Good morning, everyone. I'd like to welcome you to my final presentation for the Concrete Building Detailed Design project. Before beginning, I would like to briefly outline the structure of my presentation. I will start by introducing the key project constraints that guided the development of the two design schemes. I will then present these schemes, compare their merits, and identify the ones selected as the final design. Following this, I will address the main challenges I encountered in the analysis and design of the final scheme. Finally, I will conclude with an overview of the research component. Before developing any schemes, I first identified four key project constraint categories that guided the design process. The first design constraint was the site's proximity to a marine environment, which had a strong influence on material specification and concrete and cover requirements. Following that, the basement parking requirements shaped the grid layout and drove the need for efficient floor and transfer systems. Closely linked to parking, the architectural requirements of both the retail and residential segments shape the building form to maximize comfort for all stakeholders. Having now touched on all governing constraints, the following two design options were developed. Design option 1 introduces three raking columns along the sloping facade, two running from level 2 up to level 18 and one from level 2 to level 11. This arrangement allows for slab spans of up to 11 meters at the podium level. A key feature of this option is the complex transfer beam system at level 2, which permitted thinner slabs above. Within the podium, slabs were proposed as traditional flat slabs, except for level 2, which was post-tensioned. An additional idea explored was a raking member at level 2 partitions to relieve axial load on the transfer beams. Above the podium, ordinary flat slabs were used, while levels 18 to 22 adopted a conventional beam slab system. Using the Economic Frame Guide and Tekla Structural Designer, the proposed elements for design option 1 were sized. Starting with slabs, levels 0 and 1 were designed as 300 and 350 mil flat slabs respectively. Level 2 was a 400 mil post-tension slab. From levels 3 to 18, 250 mil flat slabs were used, and from levels 18 to 22, 250 mil solid beam slabs were adopted. Moving on to columns, three different sizes of columns were adopted in the design, including 600 by 600, 800 by 800, and 1000 by 1000 rectangular column sections. On level 2, as shown in the schematic, two types of standardized transfer beams are identified, a very deep 800 by 2500 mil section and an 800 by 2000 mil section, which were distributed as shown depending on the planted columns they supported. Like level 2, level 18 had a standard dimension transfer beam, which was sized as 800 by 1200 mil deep sections. Having reviewed the sizing for option 1, we can now turn to the vertical load paths of the design. Starting at level 22, loads are carried by the beam slab system and transferred into reinforced concrete columns. These columns pass axial forces down to the level 18 transfer system, which redistributes them onto a new column grid. The loads are then carried further to level 2 transfer structure, where transfer beam TB3 is supported by secondary beams rather than directly by columns. Finally, all loads are transferred into the foundation system, with reactions in the form of axial forces, moments, and shear, depending on the chosen foundation scheme. Now moving on to option 2. Option 2 uses a hybrid system. Flat slabs in public areas for headroom and beam slabs elsewhere for efficiency and MEP coordination. From the basement to level 2, the north side uses flat slabs and the south side beam slabs, with a transfer system at level 2 reducing spans to 8 meters. Levels 3 to 9 use beam slabs throughout, while levels 9 to 18 adopt a mix, flat slab to the north and beam slabs to the south. Between level 9 and 12, raking columns are interrupted to provide open views before being reinstated. At level 18, transfer beams allow conventional beam slab construction up to the roof. At levels 0 and 1, 275 mil slabs are used, with beam slabs of the same thickness supported on 400 by 700 mil beams. From levels 2 to 18, the slab thickness remains 275 mil, while the beam increase to 400 by 750 mil. Like option 1, the same standardized size of columns is used throughout the scheme, depending on the load demands of each region. And in the same way, The transfer beam at level 2 was sized as 800 by 2000 mil, while the transfer beams at level 18 sized as 800 by 1200, shallower than those of option 1, given reduced demands. The vertical load path of design option 1 and 2 are quite similar. However, it is important to note that due to the presence of raking columns in both options, the resulting force components induced by the incline must be considered for global lateral stability. In both schemes, the core is modeled as an RHS cantilever with the required openings. It is designed to resist multiple actions, while the slab acts as diaphragms to transfer forces. Both the core behavior and diaphragm action will be addressed later in the presentation. Now that both schemes have been presented, we can compare them against several criteria, with the most important being cost, sustainability, and buildability. In terms of cost, Scheme 1's superstructure is estimated at £2.7 million, compared to £3.3 million for Scheme 2, a significant increase. This trend continues with embodied carbon at stage A1, where Scheme 1 shows 24% less than Scheme 2. However, benchmarking is needed to put these numbers into context. According to a study by Arup, new builds must target less than 200 kilograms of embodied CO2 per square meter to align with the UK's 2050 net zero goals. As shown, Scheme 1 performs far better than Scheme 2. And this trend also carries forward when looking at a complete stage A1 to A5 analysis. In terms of buildability, option 1, mainly flat slabs, allows fast cycles, simple formwork, and safer repetition. Only level 2's PT slab and the penthouse beams add local complexity. Option 2 with beam slabs is slower, needs more formwork and labor, and tighter tolerances, though it gives clearer load paths. Takeaway? Option 1 is quicker and simpler to build overall. Therefore, when combining all criteria into a decision matrix, it is clear to see that design option 1 is better than design option 2, therefore selecting it as the final design option. Before we move on to the design calculations, I would like to summarize 3 design changes I made based on feedback from the tutorials carried out. Firstly, the beam slab arrangements at levels 19 to 22 was altered to a flat slab arrangement. Secondly, the proposed PT slab at level 2 was changed to a waffle slab to avoid needing a specialist contractor for only one floor of the entire building. Lastly, the proposed raking member at level 2 was removed due to its implication to lateral stability under reversible wind actions. 9 calculation packs were developed for the detailed design of the selected scheme. First, the podium deck design. 2 questions drove the work. Can a waffle slab be designed transparently by hand and verified with a shell element FE model? And 2, how do we control the high negative moments where transfer beams coincide with waffle spans? These issues shaped strip design, FE checks, and local detailing. To address these, I analyzed the podium deck with coefficient methods, equivalent frames, and a Tekla FE shell submodel. I assumed the transfer beam beneath the longest spans acted as a support, so reinforcement was governed by span and hogging moments, not by local planted column effects. When designing along grid lines B and 11, I found that standard coefficients sometimes gave higher sagging moments than equivalent frame or FE models. So I chose design forces conservatively without being excessive. Punching shear checks aligned well across methods, typically within 5 to 6%. Once the design was complete, the waffle slab was detailed in accordance to guidance from the iStruct and TR64. For the transfer beams, the challenge was whether to use standard design or strut and tie, and how best to define design actions. After reviewing codes and case studies, I chose conventional design with forces taken as the envelope from stage construction and Tekla's 3 analysis methods. Following that, the transfer beam was detailed accordingly. Next, the inclined columns. The key challenge was validating their forces split into slab tension and compression. I checked the global Tekla model against smaller 2D and 3D submodels, which confirmed where the slab diaphragm was in tension and where it was in compression. Finally, using Tekla stress contours of the podium deck, I checked whether the existing flexural reinforcement could carry the slab tension from inclined columns and made targeted adjustments where necessary. The inclined columns were designed as ordinary columns utilizing the design forces from Tekla and validating them using simple inclined portal frames. Foundation and retaining systems were selected and sized in detail, which can be found in the design report itself. I'd like to now move on to the final part of my presentation, the research component, focusing on reinforced concrete shear cores, the backbone of tall building stability. I explored their behavior through three strands. First, comparing simplified stick models with detailed FE shell models. Second, assessing how openings affect stiffness and serviceability. And third, testing mesh sensitivity to balance accuracy with efficiency. When comparing FE shell models to stick models, the first step was developing each model following established guidance, specifically Arab Document 8 and the iStruct guide on lateral stability. This ensured both models were built on consistent principles, allowing fair comparison of their predictions. Alongside the guides, I also cross-checked Trimble's Tekla documentation to make sure the solver setup aligned with these principles. This gave confidence that both the stick and shell models were developed on sound and consistent assumptions. Loading was critical to get meaningful results. For the stick model, vertical loads were applied as point loads, while in the FE shell model, they were spread as area loads on the diaphragm plate. Lateral actions came from wind, notional loads, and extra axial forces from inclined columns. To capture twisting under wind in the east-west direction, equivalent point moments were added to both models. To test the models at ULS, I extracted and plotted compressive and tensile stresses. Two key load cases were chosen, one driving maximum compression and one driving minimum compression, effectively tension. This gave the full envelope of stress response. As a benchmark, hand calculations were also introduced, allowing me to contextualize and validate the numerical results. This stress check was repeated for both principal directions, with wind acting north-south and again east-west, to capture the full response of the core under realistic wind loading scenarios. At ULS, all models predicted the same overall picture, compression in the north-south direction and tension with higher stresses in the west-east span. But when you look at the numbers, the FE shell model consistently gave higher stresses, about 11% above the stick model and nearly 18% above hand calculations. For minimum stresses, effectively tension, stick and hand approaches underpredicted by as much as 23%. These differences, while not extreme, are meaningful. They have a clear explanation. Simpler methods smooth out shear lag, warping, and stress concentrations, while FE shells capture them directly. The message is that stick models and hand calcs are excellent for speed and intuition, but only shell modeling reveals the critical load demands that ultimately govern safe and robust design. Moving on to SLS, figure 34 shows deflections against the h/500 limit. In the north-south direction, the stick model underestimates deflection up to level 17, then slightly overpredicts. In the west-east direction, the FE shell model consistently gives higher values, while the stick model even shows a strange drop after level 18. Figure 35 highlights these differences, showcasing that while overall trends align, the stick model misses key local effects the shell model captures. So, to conclude, the choice between FE shell and stick models really depends on the project aim. If strict deflection control is critical, shell models capture wall behavior more realistically, but stick models aren't unusable. Their reliability depends heavily on stiffness factors and how connections are modeled. The unusual deflection trends we saw highlight this sensitivity, reinforcing the need to test alternative arrangements to ensure robust predictions. Turning to the final strand of the investigation, the influence of wall openings was assessed by comparing two shell models, one including openings and one excluding them. The results showed a significant impact on predicted deflections, with differences reaching up to 60%. This highlights the critical importance of explicitly modeling openings, as their omission can lead to a substantial underestimation of structural response. The final strand of the investigation examined mesh sensitivity. As shown in figure 38, reducing the quad-dominant mesh size from 5 to 0.1 meters resulted in only a modest change in total deflection, with a maximum variation of 7%. This aligns with previous sensitivity studies by Trimble, indicating the structural response converges well before the finest mesh is reached. However, as figure 39 illustrates, the computational cost increases exponentially with refinement. The 0.1 meter mesh requiring orders of magnitude more runtime. This emphasizes the need to balance marginal accuracy gains against sustainably high processing demands when selecting mesh density. Stick modeling and FE shells have consistently proven to deliver equivalent result, a fact demonstrated for decades, even in an era with far less computational power than we have today. But when dealing with more complex core geometries, precision and fine-tuning becomes critical, as even small variation can influence both ULS and SLS outcomes. Beyond this, the study highlighted the crucial impact of modeling openings within the shear core, as well as the practical implications of selecting an appropriate mesh size depending on the stage of the design. Altogether, these insights reinforce that accurate modeling is not just a tool, but it's the foundation of reliable and efficient structural design. I would like now, I would like to now leave you with a final video proposal for the 22-story tower, as well as open myself to any questions. Thank you very much for listening.